Hey everybody, Dr. A here, and in this video we're going to be exploring another example of vector rectangular components. So let's go ahead and get started. In the given information, we're being asked to determine the magnitude and direction of the resultant force. And then we're being asked to measure the orientation angle counterclockwise, that's CCW, from the positive y-axis. So what that means is once we find that resultant force vector, we're going to start here at the positive y-axis, which is shooting up from the origin, and we're going to measure our resultant angle counterclockwise to wherever it lands. Okay, so let's go ahead and get started with the solution. Now, here's my question to you. When we analyze these kind of problems, what notation could we use? Well, we could use scalar notation or vector Cartesian notation, okay, or Cartesian vector notation. So which one is better? Well, they both get you the same result at the end. It's just how we write it is what's different. Now, we've said in some previous videos, for two-dimensional vector analysis, normally we find that scalar notation is more convenient. And then for three-dimensional vectors, which we have not gotten to yet, we find that Cartesian notation is more appropriate, okay? Now, for this particular example, I want us to just practice Cartesian notation. Although, like I've said before, scalar notation would probably be a little simpler and more clean to do, but for the sake of practicing Cartesian vector notation, let's do it that way, all right? So for Cartesian vector notation, what we do is we write a resultant force vector as the x component of the resultant, frx, times a unit vector I, plus the y resultant, fry, times a unit vector j. All right, now how do we get frx? Well, we're going to say frx is going to be equal to the sum of all of the x components in that system, all right? And so what we do is we add up the x components of the 15 kilonewtons with the 18 kilonewtons, okay? And we got to be careful that we pay attention to what quadrants they're in, all right? So let's go ahead and write this out. So if I start with the 15 kilonewtons, I'm going to say 15 kilonewtons times 6/10. That gets me the cosine of this interior angle right here. And how do I know it's 10? Well, by Pythagorean theorem, this is a 6, 8, 10 triangle, which is really the same thing as a 3, 4, 5 triangle. Now I need the x component of this 18 kilonewtons here, which will be negative. So I'm going to say minus 18 kilonewtons times the cosine of 30 degrees. And if I punch all of this through, I'll get negative 6.588 kilonewtons. And all that negative means is that I've got 6.588 kilonewtons pointing to the left, okay? So that's the x component of the resultant. I'm going to do something similar for the y component of the resultant force. I'm going to say it's the sum of the y components taking things pointing up as positive. And I'm going to say 15 kilonewtons times what? It's going to be times 8/10. And then I'm going to say minus 18 kilonewtons times what? Times the sine of that 30 degrees. And I get a positive 3 kilonewtons, which really means that that y component is pointing upwards. So if the x component of the resultant is pointing to the left and the y component of the resultant is pointing up, then what quadrant are we in? Well, we are in quadrant 2. So I can go ahead and sketch some axes here. And I'm going to be able to sketch that. Draw that a little better for us. It's getting worse. There we go. That I've got a resultant force here. All right. Now, what are the components here? Well, I've got the X component, which is that 6.588 kilonewtons pointing to the left, and I've got that Y component, which is 3 kilonewtons up, all right? And you could put a little note here, NTS, not to scale right now, because this is clearly not to scale. You know, my 6.588 dimension really should be twice as long as this 3 kilonewton dimension. But it's okay to write this not to scale right now, because at this stage, you don't really know what the orientation is, although we can get it pretty quickly, right? So that orientation angle is going to be right here, right? We said it's going to be measured counterclockwise from the positive y-axis. So it's measured like I've shown here, and you know that's theta sub r. And so what I can do is I can look at this little right triangle here and do some basic trigonometry. I can say theta sub r equals the arc tangent of the absolute value of frx over fry. I'm saying frx over fry because I'm looking for this angle that's being referenced from a vertical axis, or the y-axis. And so I can substitute these values in, right? Let me wrap it around here. Theta sub r equals arc tangent of 6.588 kilonewtons divided by 3 kilonewtons, and I get a 65.5 degree angle, okay? And then I can go ahead and get the resultant force magnitude, mag Fr, by the Pythagorean theorem. That'll be Frx squared plus Fry squared. And when I punch that through, I'll get a magnitude of 50 and then square root. Let me double check that in my calculator. I wrote all this down on paper before I recorded this video, but that's 50 something, seems way too high. 6.588 squared plus 3 squared. Yep, and then I square root it. Don't forget to square root it. I almost forgot to square root it. So that's 7.24 kilonewtons. So these are my answers. Now, if I wanted to draw this a little bit better, a little bit more to scale, then I could draw this out here. And if, again, making this a little bit more correct, didn't mean to scroll there. It would look a little bit more like this, 6.588 kilonewtons, and then, you know, this is about 3 kilonewtons, and then here is my theta sub r. All right, and just for labeling purposes, we'll say 7.24 kilonewtons there. Okay, so that concludes this example. If you found this helpful, please hit like and subscribe, and be on the lookout for more content like this. Thanks for watching.